Alright, welcome to episode 3 of our differential equations part in multivariable physics. And so right now we're going to be talking about solving first order linear ordinary differential equations. And so what that looks like is this is going to look like this, right? So we have some p y prime plus q y plus some g, or not plus g, this is going to be equals some g. And so what I'm going to do is I'm just going to normalize this. So I'm just going to say, okay, p over q, which is equal to p, and then p over g, or g over p, sorry. Let me redo this. Q over p is equal to p, and then g over p is equal to small g, so small p, small g. So what that's going to do is I'm just going to transform this into this equation, y equals small g. And one thing to note is all of these, p is a function of t. So we have p of t, g of t, we also have y of t, right? So these are all functions of t, right? Could be x, could be whatever. This is just single variable functions, okay? So let's think about how we can find solutions for this. This is a very, very simple equation. So there's a few ways. The first thing we're gonna do, okay, is we're just gonna look at the case where g is equal to 0. So in this case, when we have the equation y prime plus p of y is equal to 0. Anytime we have some differential equation, ft of y equal to 0, this is called homogeneous or homogeneous. This is this has a slightly different meaning, but as we'll see later on, but for now this is fine. So what can we how can we solve this? Well, the first thing we can do, okay, is we can think about actually, you know what, there's actually an even simpler solution here. Let's think about this. So this is still relevant, we'll come back to that, but let's just think about how would we even think about solving these. Let's just think about this equation. Let's say p is equal to 0. Well, then now we have this equation, y prime, I'll do it in purple, y prime equals g. How are we going to solve this? Well, this is pretty much what we should know how to solve this in calculus, right? We have the derivative of y is equal to some function. Well, we can reverse that by taking the antiderivative, right? So we can find y is equal to the integral of g t dt, right? That's what that's going to give us, right? So that's gonna give us some way of thinking about that solution. So we want to kind of find some way to use integrals to solve this. So let's start doing that. So first thing we're gonna do, one thing we know, if y is congruent to 0, or if y is just equal to 0 everywhere, that's a solution. But we want to look for other, more interesting solutions. So what I'm going to do is, well, if we separate this, if we take y prime equals negative py, so we move this to the other side, what we can do is you can actually divide by y here, and we'll actually get this. We're going to end up getting y prime over y is equal to negative p. And this might not seem helpful at first, but then what we can realize is, wait a second, let's just think about this. Let's think about, well, what is, d over dx, right, of the natural log of u, well, that's u prime over u. Right? So if you remember your differentiation rules, right? So let's just try taking the derivative here, or the antiderivative, right? If we do that, we're going to find that we can actually you get the natural log of y is equal to, and then we have this integral of minus p t dt, right? But this still is in the solution. Obviously, we have the natural log of y is equal to this, but we want to know what y is equal to. So we can reverse this by taking by raising both sides to the power of e. So we get e to the integral of negative pt. Right. So I know this looks weird, we're raising e to the power of some of an integral, but realize that this doesn't make too, like, if you follow the logic here, it's just what it ends up being. And in practice, this isn't some abstract function. Like, we'll actually have a pt here that we can differentiate, so it actually does kind of make some sense when we actually see it in practice. And one other thing we can notice is we have this, we want to get rid of this ill, right? We have an absolute value. How can we look to do that? Well, one thing to notice is that e to the power of anything is never e to the power of x, whether it's positive or negative, is never less than 0. So it is never less than 0. It is always positive. Maybe I should just write it like this. It's positive everywhere. So this absolute value is, it doesn't matter. We can remove it. So then we get y equals e to this integral. And then one more thing is that, well, we have this integral, we want to add a plus c here. But this plus c, you know, we can take our differentiation rules, and so we can actually write e to the power of c, e to the power of our integral. Right? And this is also a constant, so we can just say that this is a constant. So we've ended up finding the solution here, and the solution is y is equal to some constant, I'm just going to say a, e to the power of negative integral, or the negative antiderivative of pt. So that looks kind of bad. Negative antiderivative of p t dt, and that's our solution, right? And so I was thinking of talking about how we can solve the general case, and this general case when g is not equal to 0. So what happens when g is not equal to 0? We can still use the same thing. So I'm going to talk about two ways to do this. And the first way is to use variation of parameters. And I don't know if I might have enough space. I might. Maybe if I get creative. So variation of parameters. So what does this look like? What we're going to do here is we're going to say, suppose we have some y. Suppose y is equal to u, okay, times y1. And then y1 is going to be, y1 is a solution. Okay, a solution to y prime plus py equals 0. So what all that's saying is y1 is equal to a times, well, actually, we don't even need to worry about the constant. We can just say it's equal to 0 because it's just some arbitrary solution. P t dt, right? So how does this help us? Well, let's do a bit of substitution here. So let's think about, okay, well, if we do this, what is y prime? Y prime becomes u prime y1 plus u y1 prime, right? Use the product rule. And now we can, and actually the reason it's called variation parameters is because this parameter u is meant to vary. But let's go back into solving this. Now we just sub. So let's substitute this in. So we basically take u y1 prime plus p u y1 is equal to g. And what do we get? Well, we get, u prime y1 plus u y1 prime plus p u y1 equals g. Well, we can actually separate this out. This becomes u y1 prime plus p y1 is equal to g u prime y1. But wait, we just said that y1 is a solution to this equation, right? So this is actually 0. So this becomes u y1 is equal to g. U prime y1 is equal to g. So u prime is equal to g over y1. And then what we can do is we can solve for u. And then we know how to solve u, where u is just going to be the integral g over y prime y1. And then, well, what's that going to mean? Well, okay, so we also have to consider dt, and then we also have to add our constant. So I'm going to add that in green. Plus c. Don't forget your plus c. The next step. Okay, now remember, we haven't solved this. We've only found u, and we already know what y1 is. So you have to combine this. We go y is equal to u y1. Well, this is going to be equal to this e to the power of negative p t dt times g over y1. So g over actually g is e times the integral of pt dt times gt dt plus c. Right, I'm gonna put big brackets around it so you can see it easily. Right, and so this is our solution to y. This is the solution for the general equation y prime plus py equal g. All right. Hopefully that makes sense. Yes, I think that should be good. This episode's a bit long, but we kind of went over how to solve that. So let me know if anything doesn't make sense, and I'm going to move on to another quick alternative way of how to solve this. And then I think we'll talk about proving the existence of these things, and then maybe some more solutions before we finally move on. So that should be everything.